Hello everyone, today we're going to be talking about writing in scientific notation. Let's start off with our warm-up. Pause the video when you're done, unpause, and we can go over it. Okay, so yes, it is true. So this equation is true. 1.5 times 10 to the 6th is 1,500,000. All right, we could see that by doing 1.5 times 10 to the 6th, which is 1 million. And we can use a calculator if we wanted to see that it equals 1,500,000. Excellent, very good. The 6 does not represent the number of zeros, but the number of place values. A lot of people think, oh, that's the number of zeros. You just add 6 zeros, but that's not true. It's the number of place values. Okay, so here's our definition of scientific notation. A positive finite decimal s is to be written in scientific notation if it is expressed as a product of d times 10 to the n, where d is a finite decimal, so that 1 is less than or equal to d, and d is less than 10, and n is an integer. N is called the order of magnitude of the decimal d times 10 to the n. So let's break this up a little bit more. We have something in the form of d times 10 to the n, similar to what we had from the beginning, 1.5 times 10 to the 6th. So d times 10 to the n is our number. D needs to be something specific in order for it to be written in proper scientific notation. D must be a finite decimal. A finite decimal means a decimal that stops. In other words, it's opposite of infinite. It does not go on forever, it stops. So for example, 1.5 in our warm-up is a finite decimal. The second most important thing is this mathematical statement. This is saying that d must be in between 1 and 10. It can equal 1, but it cannot equal 10. So we could say that d can equal 1, but can't be 10. And it must be in between 1 and 10 in order for it to be proper scientific notation. So let's take a look at examples. Based on this definition, are the following numbers written correctly in scientific notation? Explain your reasoning. So let's take a look at 18 times 10 to the 4th. Our first number is what we need to be looking at, that 18. That's our d in this case. And our d must be a decimal or a whole number, that still counts. And it must be in between 1 and 10. Is 18 in between 1 and 10? No. So no, this is not written in scientific notation. Because 18 is greater than 10. That doesn't work. It must be in between 1 and 10. So that first number for all of these must be in between 1 and 10. I want you to pause the video, try the rest on your own. Unpause it when you're ready. Okay, so that first one is yes, and that's because 5 is in between 1 and 10. The second one, yes. 7.56 is between 1 and 10, right? Think of it as money. $7.56 is in between $1 and $10. Next, we look at that 75. That is no, because 75 is greater than 10. Next one, look at that 0.5. No, it is less than 1, right? A half is less than 1. It's kind of like 50 cents. It's less than $1. So, no, it is not written in proper scientific notation because 0.5 is not in between 1 and 10. Remember, that first number is what we're really looking at. Next one, 21. No, it's not, because 21 is greater than 10. Excellent. Now let's do some examples of writing in scientific notation. Attached to the assignment, you should see this reference sheet. This is your notes. This is what you're going to use when you're writing numbers in scientific notations. You're going to change large numbers into scientific notation, changing small numbers into scientific notation, and changing back to standard form. So let's take a look at this first example here. Mercury is 65,594,000 miles from Earth. How can we write this in scientific notation? So what we want to do is we want to take that number and we want to rewrite it. Now we're dealing with a really large number, and we want to write it into scientific notation. So if we go back to our notes here, we're going to be using this beginning. Move the decimal to the left to make a number between 1 and 10. So we're actually going to go to the left here and move the decimal. First is we need to place our decimal in between two digits to make it in between 1 and 10. So right now we have an invisible decimal. Our decimal for our whole numbers is always at the end here. We want to move it. What position must we move our decimal in order to be between a number 1 and 10? Right here. If we put our decimal here, we have 6.5594. That's where we want our decimal to move. So in the instructions, we're going to move our decimal where it is, the green one, to the left and count. 1, 2, 3, 4, 5, 6, 7. 7. So we rewrite our number as 6.5594 times 10, and our exponent is the number of spaces we move to the left, which is 7. Done. Let's take a look at the second example. I want you to try number 2 and 3. Sorry, there's a little typo, as always. Standard. So I want you to try number 2 and 3. Pause the video. Unpause it when you're ready to go over it. Okay, number 2. A certain human red blood cell has a diameter of 0.000007 meters. Which expression represents the diameter in meters in scientific notation? Right away, we can get rid of C and D. The reason we can get rid of C and D is because there's positive exponents and only negative exponents are really, really small numbers. So let's take a closer look at our number. So we have 5 zeros, 7. A lot of people might choose B because of the 5 zeros, but that is not necessarily true. If we go back to our notes, it says that we must move the decimal to the right this time in order to create a number between 1 and 10. Our decimal point is already there, shown. And we want a new decimal point, which would be after the 7, to make a number in between 1 and 10. So we are going to count. 1, 2, 3, 4, 5, 6. That means it's 6 times 10 to the negative 6, and it's negative 6 because it's a really small number. Our answer here is A. Last, we have 3 times 10 to the 8. This you could easily do with a calculator if you wanted, but we're going to do it using our notes. So we have to identify where our decimal point is, which is right after the 3. This 8 indicates that we are moving 8 place values to the right since it's positive. 1, 2, 3, 4, 5, 6, 7, 8. We fill in those place values with zeros, and we are left with 3, 0, 0, 0, 1, 2, 3, 4. Add our commas, and we have 300 million. And that's it. You're going to complete the problem set for the rest of your classwork and submit it. Have a wonderful day, and see you all later.